Thank you, sir.
Okay, Machiavello, Gosine, Lanoff, Chalut, Valius, Albina, Mitchell, Valenides, Alvarez, Lambro, Ambrine, Patel, Farber, Rambro. Okay, I guess we're ready to go. Okay, so I handed back homework 3, and most people got most credit. It was fairly straightforward if you did it. It should make everything hang together now. Some people lost a small number of points, a point or two on the graphs. I won't bother doing that here, but if I have a problem with it, you can see me. But I think I made it clear on the paper what the problem was. Especially, in particular, the graph for number 4. People just drew slanted lines instead of straight lines. Didn't actually follow the formula. Okay, I know you're in here somewhere. One thing where people lost credit, which I warned you about, let me warn you again for the next homework. This is really important. Do not, under any circumstances, use old versions of the homework. You may think it's helpful, but actually it's harmful. Because unless you're really good at copying things and know what you're doing, you're not going to get the right answers, because I changed the parameters each semester. And the different parameters give different numerical values, and the simulation and the theory do not agree. So if you can put in the effort to make sure that you took the old one and changed it correctly, you might as well not look at the old one and do it yourself. And if you can't do that, then you're going to get caught, because it's easy to spot when somebody has not used this homework. And there's no way you can get around handing in answers that are inconsistent or that come out to be the ones from the previous semester by claiming that, in fact, you talk to other people because you're allowed to consult, but you're not allowed to copy. If you got the wrong answers and the answers correspond to a previous semester, the only conclusion I can draw is that you got an old homework and you copied it. And as I say, that's illegal. The other thing is, several people did this. They wrote answers in the table that were different from the answers that they had actually computed. In fact, there were people who did it right and then wrote in the wrong answers. And apparently what they did was they looked at somebody else's who was handing it in, and then they changed the answers on their table, but they didn't change the answers in the computation. Actually, it doesn't matter that much whether the answers are right or wrong, but if the answers you write on your table are different than what your simulation actually produced or your calculations produced, again, that's cheating, because that's deception. What you're trying to show is you're fixing up the answers to be what you think are right, but they're not the answers you computed. So whatever answers you get from your simulation, whether you think they're right or wrong, those are the answers that go in the table. Whatever answers you computed for the theory, that's what goes in your table. Now, if you don't like those answers, you want to change the theory and get it right, or change the simulation, find the error, that's fine. But it's strictly illegal to run a simulation, get some answers, and then write other answers in the table. So if you did that, that's bad, and if you don't do it again. Remember, homework 4 is coming up. The same problem is there. Make sure you do your own work. Other than that, there are only a few people who did that, but I keep on saying this over and over again. Don't fall into that trap. Okay, so are there any questions about homework 3? So it should be now that this inverse transform idea and what density functions are, distribution functions, this should all make sense now. Everything should be internally consistent. Homework 4 is just an extension of homework 3, in which instead of looking at a single random variable, you add up two random variables, and so that uses the idea of convolution. So one part is new, not a big deal, but it's something that's different from the other example, and cases 1, 2, and 4 are exactly the same as before. And this one is actually easier because you don't have to draw any graphs. And that one is due, I said Tuesday, is that right? Hand it in. Yeah, sure. We're on TV. We'll make you a star. Okay, so are there any other questions about homework 4, which will be due on Tuesday? Ordinarily, it would be due today, but we didn't have class on Tuesday, so you didn't have time to ask questions about it. How many people have done it? The work? Questions?
My calculation for the random variable for the number 3.
Uh-huh.
I'm not sure I did it right.
Well, I gave you the density function, right?
Yeah.
Okay, so...
On the sheet that was...
Okay, so the question is about the inverse transform method for case number 3. So I gave you the density function. From that, you calculate the distribution function.
Yeah.
Okay, now to make sure that the distribution function is correct, you should draw its graph and make sure that it's non-decreasing, that it starts at 0 and it ends at 1. And then, so once you have the distribution function, you have a algebraic expression for it. You take that expression and you set that equal to the value r. So it'll look like this.
That's right, but I'm not sure if I got that.
Okay, in this particular case, the thing is, takes all its values between 0 and 1, I think. So here would be the distribution function for, I guess it's x2 in case 3. No, it's the distribution function, yeah, for x2 in case 3. Is that right? Okay, and it looks something like this. Is that correct?
No, it looks right.
Is that right?
It looks right.
Okay. And you have some formula for this, right? The formula is whatever that thing is. And then what you do is you take the value of r, you put it on the vertical axis, project over to the curve and down, and that's the value of x. So in other words, what you're setting is capital F of x is equal to r. And now you got to solve this backwards, because you got to find x as a function of r, because r is what the simulation gives you. And I think this is a quadratic, so you have to use a square root formula, something like that.
That's what I was wondering, if when it's a quadratic,
You end up with two square roots.
Yeah, you wind up with 2. There are 2 square roots, but one of them is negative, right?
Right, one's negative and one's positive.
Okay, so obviously the negative one can't be right because you can't project down to a negative value. So the positive one is the right one. Take the positive one. Then you, x equals the positive value that results from that equation. And then you run it, and it should agree with the theory. And if it agrees with the theory, then you're okay.
that's it, but the theory for GFT with that Q minus Q, to find the GFT.
Okay, well, when you check with the easy theory, remember that if you have 3 different things you're going to check. You're going to compare with theory: the mean, the variance, and the probability, which come from the convolution formula. And they all depend on generating the x's correctly. So it's easy to check the mean and the variance formula. So if those agree, that means that you're generating the x's correctly, and then if that disagrees with the theory for the convolution, that means you must have done the theory for the convolution wrong. If the mean and the variance do not agree with the theory, then one possibility is that theory is wrong. Another is that the inverse transform method is wrong. But the theory is easy for that, because all you're doing, for example, for the mean, is adding up the 2 mean values, one of which you've already done, which is 1/2, and I forget what the other one is, but it's simple.
Yes, the first one is from case 1.
First one's from case 1, and the second one is new, but it's easy to calculate that expected value. You add those two up, and that should give you the theoretical answer. And if that agrees then with what you get from the simulation, then you're probably doing the simulation correctly.
It agrees, but then that's if the GFT doesn't agree.
Well, if of the three pieces, two of them agree and one doesn't, then the problem is probably with the theory of the one that doesn't agree. Okay? So any other questions about this? So the course should be starting to come together now. If now you're confused, now it's really the time to ask questions. You shouldn't be confused now. My view is that the course is, it's easy to take this course and sort of get the right answers and still be confused and not know what you're doing. But when you get to this homework, then that shouldn't happen anymore. And so you're turning this corner. And if you're still confused, then you should ask questions or see me or something. All right, so if we're done with that, we were talking...
A
question, yeah.
Did you talk about case 3 already?
That's what we're just talking about. But we'll go ask your question.
Because when I plug that formula, my formula in, when I plug the variables into my formula, I get like 1.25 or 1.1.
Which formula are you talking about?
My program.
Well, remember that if you're talking about generating probabilities, probabilities always have to lie between 0 and 1. A variance can never be negative. Expected value can be anything, and a variance can be any non-negative number. So which is the one that you're getting that seems inconsistent?
My EX. My expected value
And in the simulation or the theory?
in the simulation.
And it disagrees with theory?
Wait. I
Uh,
must be just putting it in wrong.
how about the variance? Does the variance disagree?
Well, the variance is correct.
So you get the variance right, but not the simulate, not the expected value? I don't know, because if you get the variance correct, then it seems reasonable that you're generating your random numbers properly.
So, I'm wrong.
I mean, this should be straightforward. There's only two new parts. Okay, one is this one right here, and that shouldn't be hard. In fact, you really have to know how to do this, because on the final exam there'll be something like this. Because remember that one of the big points of the course is that once you understand this, you can use simulation to solve any probability problem, no matter how complicated, simply by generating the random variable values and then writing the proper logic to describe the problem, which has nothing to do with probability. So this is a very powerful technique. So you should be able to do it in any case. That's one new part. The second part is the convolution part, which in this case is directly analogous to what you did in part 1 and homework 0.
Are we using 0, 2 minus 2t and 0 for fxt?
For the density function.
Yeah.
Yeah.
Okay.
In other words, what I did is I gave you a density function for number 2 in case 3. Right, that's what we're talking about. And if you plot that density function, it looks like this. It's 2 here and 0 here. Oh, excuse me. And this would be 1. That's t. That's 0. So in other words, I made it a triangle instead of a square. So in case 1, the density function for case 1 is the uniform, which looks like that. And what you're doing is you're taking the convolution of this with that. So the only difference between this and case 1 is that instead of putting in the integral this thing twice, you put in this thing once and use that as the other one. So I'm making the smallest possible change I can make and still have something that's different. All right? Make sense? So any other questions about homework 4? So we were talking about the normal distribution, and I think I had was doing an example, and I had done some of it, and I'll finish it up. Okay, so let me erase this. And this is the example that's in Ross. And it's page 163. And it's example what he calls 5.5a. And it's an illustration of how you use the tables to look up probability values for normal populations. So for part A, well, what he says is that he says X is normal, and this is what's given. Because why X is normal, we still haven't really argued about that. I've said that you would expect often that a generic population would have a density function that would look something like that famous bell-shaped curve, and it's symmetric about some value which is called mu, which is actually the mean or the expected value. And so lots of real populations have this characteristic, and as we'll see soon when we discuss the central limit theorem, there's a reason, not just that it happens that way, but there's a reason why this is very important. Okay, so what he says in this case is suppose that X comes from a population which is normal with mu equals 3 and sigma squared equals 16. So I'll write it sigma squared equals 16, because if I wrote it just as 16, sometimes you can't tell whether I mean sigma squared, which is the variance, or sigma, which is the square root of the variance, called the standard deviation. So we have a mean of 3 and a standard deviation of 4, the square root of 16. And what we want to do is we want to calculate for part A, which I already did, the probability that X is less than 11. And then the argument is that what you do in order to evaluate this probability, because what you need to do here is you need to find the area under this curve to the left of the value 11, and that means you have to integrate this density function, which can't be integrated in terms of elementary functions, so there's a table that does it for you. But since there's an infinite number of normal populations, you can't have an infinite number of tables. It turns out that only one table is necessary. That's the standard table for the normal population with mean 0 and variance 1. And so we had a theorem, which I proved last time, that shows you how to change a statement about a random variable with an arbitrary mu and sigma squared to one with a mu of 0 and a sigma squared of 1. And so what you do is you rewrite it in terms of the so-called z function, which is defined as x minus mu divided by sigma. So this thing right here is called z, and the theorem says that this thing is normal 0, 1. So in other words, this is equal to the probability that a standard normal variable whose distribution function is denoted by a capital phi is less than this number here. So this would be 11 minus mu, which is 3, divided by sigma, which is the square root of 16, which is 4. And so that would be capital phi of 2. So now you would go to your normal table for the standard normal variable, and you would look up capital phi of 2. So now here's the table that everybody should be familiar with. So this table is in Ross on page 570, and it's in Garamati on page 488. And the table looks like this. It's in every book. And this is a table of capital phi of x. And in Ross's version, he calls this table A1, and he writes x, and then he writes 0.00, 0.01, 0.02, and so forth, 0.09. Coming down this way, he has 0.0, 0.1, 0.2, 0.3, and so forth. 1.0, 1.1, and so on. Then he goes to 2.0, and finally he winds up at 3.4. And then he has the values of the table. For example, right here he had 0.5000. And of course, what this means is that the area to the left of 0 is 50%. So here are the values of the table. 0.5040. Going down this way, this value is 0.5398, and so on. Okay, so what I want to calculate is capital phi of 2, which is exactly this value right here. That is, it's 2.00. So if you look in the table, that value is 0.9772. So that's the answer. I like to put a 0 in front. So this is straightforward. Anybody can look these numbers up in the table. Okay, case B. The question is, what's the probability that x is greater than minus 1? Okay, so right away I can rewrite that as as capital phi, and I have here minus 1 minus 3 divided by 4. In other words, I'm taking this value, but excuse me, that's not correct, because this is a greater than, and so that would be 1 minus less than. So here is 1 minus capital phi, evaluated at that value, minus the mean, divided by the standard deviation. So that would be equal to 1 minus capital phi of minus 1. Okay, but now, how do I get negative values out of this table, which only goes for x that are non-negative? And the answer is, well, you can see from this diagram, here's the standard normal density function, and here's a value x, and here's a value minus x. So you can see that the area to the left of minus x is the same as the area to the right of plus x. And the area to the right of plus x is 1 minus the area to the left of plus x. So in other words, you have this formula that says capital phi of a negative number is equal to 1 minus capital phi of a positive number. This is in the book. It's in Garamani on page 256 and Ross page 163. So Ross page 163, Garamani page 256. And again, I discussed this last time. Okay, so 1 minus capital phi of minus 1 would be capital phi of 1. Okay, so now I come over here to capital phi of 1. That's the value right here. According to my table, everybody should check out and make sure you got the same table. This value is 0.8413. 8413. So the answer is 0.8413. And then finally, I'll do it up here. I don't need this anymore. Part C. The question is, what's the probability that x lies between 2 and 7? X lies between 2 and 7. So that would be equal to capital phi, at this limit it would be 7 minus 3 divided by 4, and then subtracting off this value would be capital phi of 2 minus 3 divided by 4. And that's equal to capital phi of 1, that's what that value is, minus capital phi, and this value turns out to be minus a quarter, it'll be minus 0.25. And that's equal to capital phi of 1, that's that value, minus Now, to get this value here, which is negative, I use this formula. So this would be minus 1 minus capital Phi of 0.25. And now I just plug in those values. So capital Phi of 1 is 0.8413, which we already saw. And I have to subtract from that minus 1 minus capital Phi of 0.25. Okay, what's capital Phi of 0.25? So to get that, I go over here to my table. So here's 0.2, here's 0.05. So I come across here to this. 0.205 would be this value right there. And according to my table, that looks like 0.9798. But wait a minute, what do I have wrong here? I want to get 5, why do I have 0.5987? Did I read it wrong? 0.25. 5987. I'm not good at reading tables. Right here. 5987. Okay, so this value here is 0.5987, and then I just do the subtraction, and the answer turns out to be 0.4400. So this stuff is simple. In other words, if the question is, find the probability that x lies in a certain range, and you're told that x is normal with a certain mean and a certain variance, then all you do is change the statement to a statement about z, which is x with the mean subtracted and all divided by the standard deviation. And then that gives you capital Phi of something, and you look that something up in the one table, and that gives you the answer. So if you were taking a course in statistics for applications in some area like education or business or something of that sort, where there wasn't even a calculus prerequisite for the course, usually this is like the first lecture. Start right up at the beginning. They don't prove why this works, because in order to do that, you have to understand about integrating and changing a variable in an integral. But the rule is simple. All you do is change a statement by subtracting the mean, dividing by the standard deviation, and then going to the one table that's in every book. That's all there is to it. So you might want to know why you want to do this. So let me give an example. First of all, let me write down some numbers that everybody who works with these things remembers.
Sorry, could you hold on a second?
Yeah.
Could you just explain that last two steps
Here?
and the one above?
Here?
Yeah.
Okay, theorem says that if I want to evaluate this probability and x is normal with a particular unknown mean and standard deviation, that what I do is I change it to a statement about x minus that mean value in units of divided by the standard deviation. So, and the distribution function of that is called capital Phi. That's a standard normal distribution function. We proved that if x is normal with mean mu and variance sigma squared, then x minus mu over sigma is normal with mean 0 and variance 1, and that's what's in the table. So in order to do this, I want to take capital Phi at that value minus that value. But in order to change this to a z value, that is to the standard normal, I take the 7, subtract the mean, which is 3, divide by the standard deviation, which is 4. Do the same thing over here. So it's capital Phi of 2 minus 3 over 4. Then I do the arithmetic in there. I see that's capital Phi of that minus capital Phi of that. I look those values up in the table, and that's my answer.
I don't understand it, that answer.
This answer?
That statement right there is saying 0.8413 minus 0.4400.
Okay. This thing here, I'm going to change this.
So I understand all of that, but I'm saying computation for the last line.
Yeah, what I did here is,
What does that arrow mean?
okay, this arrow means I don't have space to write it, so I moved it up. So that's capital Phi of 1. 1 is 7 minus 3 over 4. This is capital Phi of minus 0.25. That's 2 minus 3 over 4. Then, because that's negative, in order to use a table, I have to change it so I have 1 minus capital Phi of the positive value. So it's Phi of 1 minus 1 plus Phi of capital 0.25. Okay, Phi of 1 is 0.8413 from the table, minus, parentheses, 1 minus capital Phi of 0.25. Capital Phi of 0.25 is 5987 from the table. That minus that is 0.4400. So all I did was plug in the numbers and then go to the table and look up the values in the table for capital Phi of that and capital Phi of that, and then subtract them. Okay? Okay, so here are some particular cases. Now, one thing you should notice is that in order to do this, you need to know two parameters, the mean and the standard deviation, which is the square root of the variance. So now, all this time I've been asking you to calculate the variance and saying it's a measure of spread, but there are other measures of spread, and you might say that you don't really understand what the variance is. So now it should start to make some sense, because the variance is the parameter that, or at least the square root of the variance is the parameter that defines the normal distribution. So once you know something is normal, and lots of things are normal, both because of empirical observation and also because of the central limit theorem, which we haven't gotten to yet. So lots of things are normal, and once you know something is normal, in order to be able to get numbers out, you only need to know two things, namely the mean value, which is the average, that's the central location, and the variance, which is a measure of the spread. Okay, now, the variance, that measure of the spread, since you're talking about units of in the square root of that, the square root of that is called the standard deviation. So capital Phi of 1 is the area to the left of 1 in the standard normal variable. So in other words, if this is my standard normal, here's 0, here's 1, this 1 represents one standard deviation. So the area to the left of one standard deviation above the mean, this is the way people talk, this is equal to 0.8413. Right, that's what I get if I go over here to this table. So roughly, almost 85% of the area of a normal distribution lies, is less than one standard deviation above its mean value. Then I could say this, capital Phi of 1 minus capital Phi of minus 1. So that's the area between 1 and minus 1. So that's the area that's within one standard deviation of the mean. And if I look these values up in the table, well, by plugging into the formula, this will be 2 times capital Phi of 1 minus 1. And if you look that up, that'll turn out to be approximately 68%. Or in other words, approximately 2/3. So what this says is that for any normal population, 2/3 of the mass, probability is 2/3, roughly, that a random selection will lie within one standard deviation of the average value. So once you understand that, then you can talk in terms of standard deviations. That's the way you think in terms of absolute values. Capital Phi of 2 is equal to 0.9772. In other words, almost 98%. So this means that roughly 98% of the population values lie to the left of two standard deviations above the mean. Capital Phi of 2 minus capital Phi of minus 2. In other words, this is the probability that a random sample from a normal distribution, normal population, lies within two standard deviations of its average value. And that will turn out to be equal to, if you plug into the table there, 0.9544, or approximately 95%. So approximately 95% of the values in a normal population lie within 2 standard deviations of its central value, of its mean value, regardless of what that mean value is. Capital Phi of 3 standard deviations, value is 0.9987. So the fraction of values in a normal population that lie within 3 standard deviations of the mean is equal to 0.9974, or about 99.75%. So you should make sure that you can go to the table and look these up. That is, calculate, look up that value, subtract them, and make sure that you get these values. So when you're talking about a normal population, and you're talking about this measure of spread, the standard deviation, almost all of the mass, 99.75%, lies within 3 standard deviations, and 95% lies within 2 standard deviations, and 2/3 of it lies within 1 standard deviation. So now, a typical example, a good example of IQs, of the normal distribution is IQs. So IQ scores are normal, roughly, this is the way the IQ test is designed, normal with an average value of 100 and a standard deviation of 15 points. So in other words, a variance of 15 squared, or 225. Okay, so the IQ tests are designed so that when zillions of people take it, they average out to 100, and if you were to plot the density function, you'd get a bell-shaped curve which would center at 100 and would have a standard deviation of 15. So this value right here is 115, and then here 2 standard deviations would be 130, and 3 standard deviations would be 145, and so forth. So if you ask the question then, what fraction of the population has an IQ between 115 points and 85 points? This is the so-called normal range for IQs. This is within 1 standard deviation of the mean. So roughly then, 2/3 of the population lies within 1 standard deviation of the mean. So the fraction of IQ scores between 85 and 115 is about 2/3. So 115, this is usually considered sort of college level, I think. I'm not sure that that's true anymore, but sort of the cutoff here is supposedly that this is the value. If you have the intelligence to go to college, then you're roughly here about 1 standard deviation above the mean. That's rough argument. 130, that's 2 standard deviations above the mean, and according to this, about 98%, roughly 98% of the population lies below 130, which means that about 2%, actually about 2.5%, lie above 130. So 130 is often what's considered in IQ circles as gifted. I hate that terminology, but if you have a child and you want to get him into a so-called gifted program, then one of the criteria for being designated gifted, and that gives you a better education than if you're not, at least if you're qualified to take it. That's the way the system works, is that the system yields somewhat to people who are able to get more, or actually people who need more because on the other end of the scale too. But in any event, if you're a parent and you want your child to be considered gifted and get into a gifted program, then one of the criteria is that he should have an IQ of at least 130. So what that means is that if 130 is the cutoff, then the gifted program is designed by definition to accommodate roughly 2.5% of the population, because about maybe 2% of the population, between 2 and 3%. 145, that's often called the genius level. that's 3 standard deviations above the mean. So if you have an IQ of 145 at this cutoff, the fraction of values to the left of 3 standard deviations is roughly 99.9%, or in other words, only 1 out of 1,000 is to the right of 145. So by this definition of genius, 1 person out of 1,000 is a genius. Of course, in my opinion, that doesn't really make any sense because 1 out of 1,000, it's good to be that smart, or at least it's good to have that high an IQ score because it's debatable what the IQ score really means. But in any event, if you're 1 out of 1,000, well, we have millions of people in this country. So for every million people, there's 1,000 geniuses. And if we have 300 million people, that would be 300,000 geniuses. Seems to me that genius is for Einstein and Newton and people like that, and not for 300,000 smart kids. But in any event, roughly you can see what's going on here. So it's not by chance that these are the scores that educators talk of as being meaningful. 85 to 115, that's the normal range. That's within 1 standard deviation of the mean. Gifted is above 2 standard deviations, and the genius or very gifted is above 3 standard deviations. So that's an example of the normal distribution in applications. Okay, so there are lots of easy questions you can ask about this. Like on a final exam, you should bring in a copy of this table. Of course, I probably wouldn't ask a question that just asks you to look things up in a table because that's too easy. Everybody would get it right, so you might as well just normalize it away, discount it, and assume everybody can do that. Okay, any questions about this? How many people have seen this before? This is the... Okay. All right. That was a few people for TV watchers. All right, so now I want to shift gears a little bit, and I want to make some observations. Going back to homework 4, one of the questions was that you wanted to calculate the density function of a sum of random variables, each of which is uniform 0, 1. So here's a density function that's uniform 0, 1, looks like a box. And suppose I select from a uniform population, and then I select again independently from a uniform population, and I add them up. So this is the convolution problem that you were asked to actually did the arithmetic in homework 0 and are going to use now in homework 4. So when you do that convolution, what you're doing is you are getting a new density function which represents the density function of the sum of the random variables, each of which has this density function. So let me indicate this by writing plus. I'll put quotation marks around it because you're not actually adding the density functions, you're adding the random variables, but you're taking the convolution of the density function. So when you get done, as you know, so this is what happens in homework number 4, you get something that looks like this. Here's 0, here's 1, here's 2. This now is the density function of the sum of the random variables whose density functions are that. And as you know, it'll look like this. So you go from the box to the triangle. Now we had another case. Suppose that the x's that I'm adding are exponential. So if they're exponential, then the density function looks like that. And if I add 2 of them, then I'm adding up or taking a convolution of those 2 density functions. Remember, I don't add the density functions, I take the convolution of the density functions, and the resulting integral, result of the convolution, is another density function, which is the density function of the sum of the random variables whose density functions are these. And you know from homework 0 and homework 3 that if you do this computation, that the density function you will get will look something like that. Okay, now my observation, my claim is that this density function is closer to a bell-shaped curve, looks more normal than either of these. And this density function looks closer to a bell-shaped curve or is more normal than either of these. And in fact, let's look at the dice problem. Okay, so this is where the x's are uniform, 0, 1. And this was the case where the x's were exponential with some parameter, doesn't matter what it is. Now let's take the case where x corresponds to the dice. Actually, the sum of two dice. So if I look at a single die and look at its probability mass function, it looks something like this. It takes the values 1, 2, 3, 4, 5, 6 with probabilities 1/6. So here's 1, 2, 3, 4, 5, 6, and the height of each of these is 1/6. So if I add two of them, okay, the same thing again, I won't be so careful drawing it. What I'm going to get is another probability mass function. And you know that that probability mass function looks something like this. First of all, it has the values 2 through 12. So here is 2, 3, 4, 5, 6, 7, 8. I'm running out of space, so I think what I'm going to do is do it more carefully up here. Okay, so I'm going to add up the two dice, and I'm going to get a new probability mass function. And so the values you can get are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, what are the probabilities associated with those? Remember, this is the probability mass function. So it's the probability x equals t. That's t. Now, the probability that when I roll two dice, the sum is a 2, as you know, is 1 over 36. So that's 1 over 36. The probability of a 3 is 2 over 36. The probability of a 4 is 3 over 36. 5 is 4 over 36. 6 is 5 over 36. 7 is 6 over 36. 8 is the same as 6. 9 is the same as 5, and so on. Right? So this value right here is 1 over 36, and this value right here is 6 over 36. Okay, now I claim that, in fact, this looks more like a normal distribution than either of these. Of course, they're discrete, but you can see, just like with the uniform, let me go back to the uniform. In the uniform, what I did was I added up two things that were flat, and I got this triangle. And here I'm adding up two things that are flat in a discrete case, and I'm getting this triangle. So it seems intuitively obvious that, at least in this case, that when I add independent random variables, that the result looks more like a normal distribution than when I started. Now, in fact, that's true no matter what the population of random variables is that you add up. And there's a theorem that says that if I add up in the limit an infinite number of random variables, an infinite number of values from any population, that as the number in the sum gets bigger and bigger, the resulting density or probability mass function is going to look more and more like a normal. And in the limit it will be normal, which says that sums of independent random variables in the limit are normally distributed no matter what population they come from. Now, averages are sums. So let me write this down. Okay, so this is extremely important. So what I'm doing now is I'm writing down what this observation motivated, although proving it is a big deal. Okay, so here is the central limit theorem. You can tell from the name that it's important. Central limit theorem. And in Ross, it's theorem 6.31. Theorem 6.3.1, which is on page 194. And Garamani, it's Theorem 10.13, which is on page 452. And there are various different ways to write it, so I'm going to write it several different ways. Here's what Ross says. He says, let x1, x2, and so forth be IID. This is an abbreviation, stands for independent, identically distributed. In other words, IID random variables means that I am going to sample independently over and over again from the same urn, identically distributed. Okay, so we have these values. This is the first value I draw out of the urn, that's the second value I draw out of the urn, and so forth. And he says, consider, and let's say that they have an expected value, which he will call mu, and a variance, which he calls sigma squared. I don't have to write a subscript here because remember they're identically distributed. They all come from the same urn. So in other words, the long run average of these x's is mu, and the variance of those x's is sigma squared. Then he says that the central limit theorem says this. The central limit theorem says that x1 plus x2 and so forth up through xn minus n times mu divided by sigma times the square root of n, that this thing is approximately, right, like this, approaches something that is normal with mean 0 and variance 1. Let me write it again over here a different way, a way that I like better. The central limit theorem says this, CLT. For a large n, large enough sample size, x bar of n minus e of x divided by the square root of the variance of x divided by n is normal, or approximately normal, 0, 1. Now this thing is the same thing, because let's take a look at this. If I divide numerator and denominator by n, then I would have x1 plus xn over n minus mu divided by the square root of, well, let's see, I'll write it as divided by sigma divided by the square root of n. And now I can take the square root sign here and write that as sigma squared, and then that would be exactly the same as this. Because this thing here, the sum of the x's divided by n, that is by definition the average, x bar over n. This piece right over here, that's by definition the expected value, and this piece right here is exactly the same as the square root of the variance divided by n. So there are different ways to write this thing. But when you look at it in this form, which is what I like, what this says is that the average value, if you subtract off this constant, which is the expected value, and put it in units, which are the square root of the variance divided by the sample size, that result is a sample from the normal population. So what that means is that averages are normally distributed, roughly, are normally distributed for a large n. In other words, if I take my sample size large enough, then and calculate the average value, I can view that average value as something that comes from a normal population, regardless of what population I'm originally sampling from. Because what is an average value? An average value is a sum divided by a constant. So as we saw, since sums tend to be normally distributed, that means that average values tend to be normally distributed. Because all you do when you go from the sum to the average is divide by a constant. That just fixes the size. So that says this amazing fact. It says that if I take a convolution of two things, and then take the result of that and take the convolution again, and then take the result of that and take the convolution again, and I do that over and over again, no matter what I start with, the answer will always be the same. It'll always be the density function for the normal distribution. Okay, because let's go back here, let's look at the sum. x1 plus x2, and so forth. This is the key, because in the original statement right here, there's the sum of the x's. This is just a constant, this is just a constant. So this is like the z factor. Okay, so what this says is that if I take the convolution of that, and then take its result, and put that in the back of the integral formula for convolution, and take the convolution of this result with this one, and then do it again and again and again, that no matter what I started with in this integral formula, if I do it over and over again, the end result will always be the same. It'll always approach the formula for the normal density function. The only parameters that are in here are the mu and the sigma. So if you know the mean and the variance, then you can calculate the probability that the average value will have any particular values you want, no matter what population it is that it comes from. So mathematically, this is amazing, because it's very difficult, if you think about it, first principles, to prove that if I'm going to go through this complicated convolution argument, let's go back to this convolution. Take the integral from minus to plus infinity of a density function, let's see, evaluated at t minus u, times the density function evaluated at u du. Okay, when I get done, I get something else, which I've called g. Okay, now what this thing says is that now let me take this g, and put it in there, and evaluate that. And if I call this G1, that'll give me G2. Okay, so this is G1. And then what I do is I take this, and I take the G2 and I put it in here, and I get G3. And so on. I do this forever. And what the mathematical theorem says is that no matter what you put in here, if you just do this forever, the end result, the Gn, and I'll write it here, Gn of t, in the limit, as n goes to infinity, is equal to 1 over the square root of 2 pi e to the minus 1/2 t squared. So no matter what I start with, I go through all of this stuff, and then I do this over and over again, and I get the density function for the standard normal variable. Okay? Now, if that isn't amazing, I don't know what is. That's a real important mathematical theorem. But it's also very practical, because what it says is that if I want to sample from a population, and I really know very little about the population, if I can just figure out its average value and its variance, then I can make probability statements about it, even though I don't know what's in the population. As long as the n, the sample size, this n right here, is big enough. The mathematics says it has to be infinity, but for practical purposes, as we'll see, because that's the next homework, you can actually work this out. It's really very simple, and you can see that if n is a number like 100 or so, or sometimes even less, then the central limit theorem works fine. So basically what this means is, essentially, average values are normally distributed. And all you have to know is the mu and the sigma. And since normal distribution with any mu and sigma is described by one single table, that means that that one table for the standard normal variable has applications to just about everything. So then the question becomes, in order to be able to use it, you have to know the mu and the sigma. Now, for the purposes of our example, since we'll start out with a specific f, then of course you know what the mu and the sigma are, so that's just an example that checks to see that it works. But in actual applications, you have to figure out by sampling, by somehow estimating the mu and the sigma, and that's what the subject of statistics is about. So maybe I should mention that now. What we've been studying up to this point is really what you would call probability. So here's probability. And so it goes along like this, but then it sort of reaches a point, and that point, that cutoff point, maybe is the central limit theorem. And then it branches out. So you can continue along the upper path and do more probability. That is, you can study probability, and this stuff can go on forever. Just like any other subject, you can get deeper and deeper, so if you're a specialist, you can it just never ends. There's always more to know, and in fact, the more you know, the more questions there are that remain to be answered. The other viewpoint is that at this point, when you get to the central limit theorem, then instead of simply asking probability questions, you're asking questions about determining the parameters of an unknown population in order to be able to apply the central limit theorem. So then the question is, given some observations, what can I say, for example, about the mean and the variance of the population I'm sampling from so I can apply the central limit theorem? So that is the start of what's called statistics. So statistics can be viewed as an application of probability, which just takes a different viewpoint than the original viewpoint. In other words, statistics, you sort of look at things backwards. Because in probability, the question is, you say, I have a certain population. Now, given that population, what is the probability that such and such will happen? In statistics, you say something like, well, in order to use this probability stuff, I have to know something about the population, and if it's a real population, not something that has been made up in a theoretical sense, then how do I know what's in that urn? How do I know what that population is? So what you try and do is you try and make some observations, and then using those observations, you try and go backwards and ask what must have been in the population, or what might have been in the population, to produce the observations that I saw. So with statistics, in fact, we already saw this with with Bayes' rule. Bayes' rule is an example. In Bayes' rule, the idea is that you have made an observation. Let's say in the example that we used, somebody is taking a HIV test and he tests positive. That's the observation, and the question is now, given that, what's the likelihood that that observation was caused by something else? In the age problem, the question you're asking is, what's the probability that the observation of a positive test was caused by the person being infected with HIV as opposed to an error? But the point is that in statistics, you design things so that you observe something and then try and figure out what caused the observation. In probability, you assume that the population has some particular characteristics, and you try and predict what it will produce if you then perform the experiment. So we've been doing this, but now we could branch into this direction or continue in this direction. And I want to do a little bit of both of those. Okay, maybe this is a dumb question, but are there any questions about this? All right, let me look at homework number 5, which the homeworks are now getting easier, I think. If you look at homework number 5, you'll see it's really simple, although it looks complicated at first. Okay, so I want to impress on you how important and how useful the central limit theorem is. This is why everybody studies statistics. In fact, when you look at all of these things that you read in the newspaper about cholesterol testing or about sample surveys, is always in the paper. 53% of the people favor Bush's war policy. This month and last month it was 51%, plus or minus 3 percentage points. And you say, what is this plus or minus 3 percentage points? What does that mean? And of course, they can't explain it to you because basically the answer is, well, it comes out of the central limit theorem. So in fact, all elementary applications of statistics, all of these sample surveys are based on the central limit theorem. And I'll explain that. Okay, so here's the question. This is homework 5. Central limit theorem. And what we want to do is this. We're going to take 3 cases, which are easy because we've already done these cases. So case number 1, x is uniform 0, 1. Case number 2, x is exponential with parameter 2. And case number 3, the probability that x equals minus 0.2 is a half, and the probability that x equals plus 1.2 is a half. So in terms of calculating expected values and variances, you've already done it, so there's nothing new here. And one of the things that I'm going to illustrate is that the central limit theorem works whether the original population is uniform or exponential or even discrete. It doesn't make any difference. And the question we want to ask is this. Let xn bar be the average. So we're going to sample n times and calculate the average value. And the question you want to ask is this. What's the probability, in this case, that the average value turns out to lie between 0.45 and 0.55? Okay, now why did I pick 0.45 and 0.55? Because in each of these cases, as you know, the expected value is equal to 1/2 or 0.5. And you already know that the average and the expected value correspond to each other. In other words, the expected value is in principle what the average would be if the sample size were infinite. And you already know from homework 3 and homework 4, and in fact homework 2, you already know that this works, that this is a good observation. But what you don't know is, you don't know how close the average is to the expected value. And you don't know how large a sample size you have to take. And what this central limit theorem is going to allow you to do is going to make precise the knowledge you already have, which is that as the sample size gets bigger, it's likely that the average will get closer and closer to the theoretical expected value. So we want to see whether that's true. The central limit theorem says that, in fact, it's exactly true. And in the limit, as n goes to infinity, the average and the expected value will be the same thing. So from the central limit theorem, I want to compute the probability that the average lies within 10% of its theoretical value. Because if the theoretical value is 0.50, then 0.50 plus 10% is that, and 0.50 minus 10% is that. And so what should happen is that as n gets bigger and bigger, the probability that the average will lie within 10% of its theoretical value should get larger and larger. And to actually calculate what that probability is, we can use the central limit theorem. Okay, so here's the idea. And as I say, I'm going to write this down now. I'll go over this again later, but this is really easy. Okay, we're going to run this for 3 different cases. We're going to run it for case n is equal to 1. I'm running out of space here again. Let me write it here. Okay, here. N equals 1. N equals 25. And n is equal to 100. And for each case, what I'm going to do is I'm going to have theory and simulation. Theory and simulation. And for n is 100, the same thing. Now, the central limit theorem doesn't apply when n equals 1. The central limit theorem applies in the limit, in theory, when n is equal to infinity. But you don't need the central limit theorem when n is equal to 1, because you're simply sampling once from the population. But when n is equal to 25, then the central limit theorem will kick in. So what I'm going to do is I'm going to give you some code, which is easy, which simply samples n times, or in this case 25 times from this, adds those values up, divides by 25, and gives you a number. And then the simulation will do this over and over again, and it'll calculate the fraction of those averages that lie in this range. That's what the simulation will give you for each case. And in order to run the simulation, of course, you need the inverse transform method, but we already have it for these cases. So this is easy to do. There's nothing new here in terms of this theory. All you have to do is calculate, using the central limit theorem, the probability that the average will in fact lie within 10% of the value 0.5. And I'll show you how to do that next time. So it's very easy. You write it out. It looks complicated, but it's just like the looking things up in the table. In fact, that's what you have to do. You have to look things up in that table. So this tells you where to look in the table. You write down the theory values. You run the simulation. You observe that everything works, and then you live happily ever after. All right, so my suggestion is download homework number 5, and as usual then, I'll go over this next time, and I'll actually do the calculations in class, and then you run the simulation, and you agree that it works. And the important thing is to appreciate what this means. It means that if you're sampling from a population, no matter what that population is, uniform, exponential, discrete, no name, it makes no difference at all. If you're sampling from any population and you calculate the average, which everybody knows intuitively is the most important single value, you can view the average as itself a sample from a normal population. And so there is one table that describes everything. And what this homework will show you is that in fact it works, because you'll predict using the central limit theorem what the probability should be, and then you will see what the simulation actually gives you, and then you can believe that it works no matter what you put in, not just for the ones I'm using for an example. Okay, and it'll show you how the sample size affects the likelihood that the average is close to the theoretical expected value. Okay, any questions about anything at this point? Next time I'll try and give you what the homework schedule is. We want to get everything done. We got Thanksgiving coming up, and then reading day and all that kind of stuff. I'll have one more homework after this. This homework is easy to do. The next homework will be easy to do. You just got to think about what it means, and then that'll be the end of the course. Okay, so see you on Tuesday, I guess.